Ground-to-orbit space transportation is restricted by a strict physical limit, the chemical energy density of molecular propellants. Conventional rocketry forces the launch vehicle to carry its own power plant. The energy source and the reaction mass are intrinsically linked within the physical volume of the fuel and oxidizer. As defined by the Tsiolkovsky rocket equation, relying on chemical combustion caps our maximum specific impulse. Even highly efficient liquid oxygen and liquid hydrogen mixes hit a theoretical limit of roughly 450 seconds. That physical cap forces engineers to dedicate 90 to 95% of a conventional launch vehicle's gross liftoff mass entirely to propellant. Achieving high-thrust launch without chemical combustion requires separating the power generation from the spacecraft. We have to transform the rocket into an open thermodynamic system. Beamed energy propulsion offers a way forward. It is the physically viable mechanism for high-thrust, non-chemical launch driven by ground-captured solar energy. Our objective is to demonstrate how projecting a high-power, near-infrared beam can achieve a specific impulse of 850 seconds, significantly increasing the payload mass fraction achievable by a single stage-to-orbit vehicle. Effectively escaping Earth's gravity well dictates a strict engineering trade. We must leave the massive power infrastructure completely on the ground. Our engineering baseline is strictly defined by orbital mechanics. We must format and deliver exactly 1.0 gigawatt of net thermal power directly into the vehicle's onboard propellant. Multiplying the efficiency constraints of photovoltaic capture, storage, laser conversion, optical transmission, and plasma absorption yields a net system efficiency of 7.58%. Applying this to our 1.0 gigawatt target reveals the required scale, capturing 13.19 gigawatts of raw solar power. At the standard terrestrial solar irradiance limit of 1,000 watts per square meter, this power requirement dictates a massive primary collector surface area. The math maps directly to the required footprint. We need exactly 13.2 square kilometers of solar harvesting field to feed the optical transmitters. Once captured, this energy must be formatted for transmission through the atmosphere. The architectural trade-off is between operating at near-infrared laser wavelengths or millimeter-wave radio frequencies. We select the 1.064 micrometer near-infrared spectrum. Shorter wavelengths allow for a highly compact 2.0-meter vehicle optic, keeping aerodynamic drag penalties minimal during the ascent phase. Building 13.2 square kilometers of solar infrastructure requires intense terrestrial capital expenditure. But placing that hardware on the Earth removes thousands of kilograms of dead weight from the launch vehicle. Pushing a 1.93 gigawatt optical beam straight up through the atmosphere introduces severe thermal constraints. If the beam intensity exceeds 100 watts per square centimeter, the near-field air will violently spark into plasma, a process called dielectric breakdown, which physically blocks the beam from transmitting. This schematic visualizes our atmospheric safety margin. By diluting the 1.93 gigawatt beam to a safe 50 watts per square centimeter, the calculation outputs a required ground transmitter diameter of 70.1 meters. Generating that beam requires immense mirror resilience. The array uses ion beam sputtered coatings to survive intense thermal loading, reflecting energy upward without melting. The pointing constraints are exceptionally tight. Focusing a 70-meter ground array onto a 2-meter vehicle receiver at a 600-kilometer slant range demands 1.67 microradians of tracking precision. To hold that lock, the system runs 2.0 kHz adaptive optics, utilizing piezo-ceramic tip-tilt mirrors to cancel out atmospheric turbulence phase distortions in real time. Delivering gigawatt power to orbit requires solving a sub-microradian optical targeting problem, relying on continuous atmospheric correction to maintain the energy bridge. The engine architecture relies on a bimodal flight profile, adapting its propulsion mechanics to the changing ambient atmospheric density. From liftoff to 12 kilometers in altitude, the vehicle operates strictly in an endo-atmospheric phase, running in air-breathing pulse laser detonation mode. By utilizing ambient tropospheric air as reaction mass, the vehicle accelerates through max Q, conserving 100% of its onboard liquid propellant. The critical regime shift occurs at 12 kilometers. As atmospheric density decays below 0.31 kilograms per cubic meter, the engine transitions to injecting its internal liquid hydrogen. Transferring the gigawatt thermal load into that hydrogen requires an absorption mechanism. Solid ceramic heat exchangers melt at 2200 Kelvin, severely restricting the maximum specific impulse. To safely isolate a 20,000 Kelvin laser-sustained plasma core, the engine utilizes a rapid vortex gas flow. Meanwhile, structural mirrors survive 49 kilowatts of flux by routing cryogenic liquid hydrogen through internal cooling channels, drawing heat away before fuel injection. The engine acts as an atmospheric transformer, maximizing overall thrust efficiency by fully exhausting external reaction mass before opening its internal tanks. We can calculate the exact performance of this architecture. Inserting a payload into low Earth orbit requires overcoming a strict trajectory limit of 9,500 meters per second, factoring in gravity, drag, and steering losses. Applying the Tsiolkovsky mass ratio with an 8,335 meter per second exhaust velocity yields a vehicle dry mass fraction of 31.99%. For an 8,500 kilogram liftoff mass, this isolates the exact fuel constraint: 5,780 kilograms of liquid hydrogen propellant. This leaves a 2,720 kilogram burnout mass. We deduct the 1,720 kilogram structural dry mass, which accounts for the composite tanks, optics, and engine core. This calculation leaves a distinct 1,000 kilogram net payload. For an 8,500 kilogram liftoff mass, this results in a final payload mass fraction of 11.76%. By operating as an open thermodynamic system, the vehicle achieves a payload mass fraction roughly 3 to 4 times higher than chemical limits. The math demonstrates a clear consequence. Decoupling energy generation from onboard mass translates directly into increased structural payload capacity. These calculations are entirely derived from established literature. The parameters defining this system architecture are anchored in decades of verified aerospace engineering, not speculative physics. The 1.0 gigawatt power threshold and the 15,000 Kelvin plasma core temperatures match perfectly with historical AIAA benchmarks and NASA experimental data. We are replacing the physical limits of chemical energy density with massive, highly precise ground-based optical engineering. The operational yield is a fully reusable ground infrastructure that can execute highly repetitive, clean orbital insertions without burning heavy boosters. Formatting primary solar radiation into a coherent optical beam provides a physics-backed architecture for sustainable, high-thrust space access.